Welcome to my third video on Introduction to Constraint Logic Programming through Picat. Today's topic is recursion. Recursion is a very powerful problem-solving method that involves divide and conquer. Given a problem, if the problem is easy and can be solved directly, then we just solve it. Otherwise, we divide the problem into subproblems, recursively solve the subproblems, and finally assemble the subproblem solutions to create a solution for the original problem. Quite often, the subproblems generated during the course are not all different. If there are common subproblems, and we don't want to solve all these subproblems separately, so in order to improve the speed, we solve the first subproblem and store the solution in a table, and reuse it for subsequent equivalent subproblems. This idea is called dynamic programming. Recursion is very important in functional programming and logic programming because many functional and logic languages do not provide iterative constructs, and we have to rely on recursion to describe repeated computations. In this lecture, I will show how to define some basic recursive functions on numbers. Alright, let me start the edit. Alright, we begin with these two very basic functions. Alright, the first function is called a successor function, so x plus 1. And the second one is the predecessor function, x minus 1. Alright, so now, we have these two functions, and we also have number 0. Alright, and we are trying to implement other operations. The first one is addition. The add, so let me write the recurrence relation. 0 add y equals y, and the recurrence x plus y, this one equals x minus 1, which is a predecessor, and plus y, and then in the end we add 1 to it. So, alright, to write this in Picat, what do we do? Let's say name the function add. Alright, if the first operand is 0, and the second one is y, and then the result is y. And add x, y. Alright, we just translate this recurrence relation to this to Picat. So this will look like a successor, and then we add predecessor x and then y. Alright, so this is addition. Now let's do subtraction. Subtraction. So x minus 0. Alright, we assume. We don't consider negative numbers. So x minus 0 equals x. And x minus, this is the recursive case. X minus this one equals, so this is so x minus y minus 1, and then this one is the predecessor. All right, so the predecessor. Okay. So this is well, basically this one add minus 1, and then we add 1 to it, add a successor. Okay. So successor, and add 1 to it, add 1 to it. Okay. All right, so subtraction. Oh, I'm sorry. So the minus 1. All right. So this subtraction. So this one. All right. X minus 0. Okay, this equals x. Subtraction. X y. All right. So this one equals. All right. The predecessor. Okay, of x minus and the predecessor y and predecessor sub x minus predecessor y. Alright, so this is the translation. Good. Alright, now let's consider multiplication. Multiplication, x times 0. Okay, or 0 times y. 0 times y. Okay, this one equals 0. And x times y equals this one. Okay, basically how many times? Yeah, we use implement this by using addition. So this is x times y minus 1. What is that? Okay, no. All right, x minus 1 because we recurse on the first operand. So x minus 1 times y, and then add y to it. Okay. So this if x is 0, okay, then okay, no matter what the second argument is, so we use an anonymous variable. Okay, so the result is 0. Okay. X, y. So this one is equals add. All right, add. This is well, maybe you want to change this recurrence relation to, well, it's the same thing. Y, add y, and then multiply. This is a predecessor x, and then y. All right. So, and we started with two functions: successor function and the predecessor function. And now our computer is much more powerful, and it can do addition, subtraction, and multiplication. All right. Next, we consider division. Okay, before we consider division, all right, we need a relation called less than. All right, so let's define less than first. Okay, let's define less than or equal to. All right, less than or equal to can be defined as follows. So x 0 is less than or equal to, okay, anything, yeah, okay, y. This one is true, okay, and okay, we write it this way. This is true, okay, and this one is x is not y 0. Okay, this one is false. Okay, we write it this way. Okay, so this is false. And x is less than y. Okay, what do we do? All right, we can reduce this relation to predecessor. So x minus 1 is less than y minus 1. All right. So now, okay, we need to use a rule to define rules to define predicate. A predicate, okay, is true or false. So let's call it less e, okay, less than or equal to. So if the first one is 0, okay, the second one, all right, we don't care. All right, this one is true. So, and this one, the first one, okay, the second one is 0, okay, then this one is false, okay, or just fail, yeah, true, false. False is fine too, the same thing as fail. And less than xy, okay, then we reduce this code to predecessor x and then predecessor y. Okay, All right, we have less than or equal to. From this, we can easily have this relation, less than. Okay, so this less than x is less than y. Okay, this one can be reduced to x plus 1 is less than or equal to y. Okay, so we define this predicate less than xy. Okay, this core can be reduced to less e. Okay, and successor x and y. Alright, with these two, okay, we are ready to define division. Okay, division. Good. Division. So division, okay, x div y. We use this div. X div y. So div y equals 0 if x is less than y. Yeah, okay, the quotient. And x div y, okay, equals, then what do we do? Okay, we implement the division by using subtraction. Alright, so it is we subtract 1y from x and then continue. Yeah, so x minus y and then div y, and each time we do one subtraction, we add 1 to the quotient. Yeah, okay, add 1 to the quotient. So that's division, right? So no, okay, now we are ready to write this function. So since div is a built-in function, we are not allowed to define a predicate named div. So let's name it my div. All right, so my div xy xy. All right, so this one is if x is less than y, this is a condition, x is less than y. All right, then the result is 0. And okay, this is the syntax. Okay, so we have, this is like something, okay, we have this function equation, and if this condition is true, and this arrow means where, okay, where basically there are no further conditions. Okay, so, and my div xy, all right, equals otherwise, okay, it equals successor. All right, so then we use subtraction. My div, all right, this is a subtraction sub x, y, and y. All right, that's division. Okay, similarly, we can have modulo. Yeah, modulo. And modulo, it is, okay, let's say x mod y equals x if x is less than y. Yeah, and x mod y equals, okay, now we find the modulo. Okay, again we do subtraction. All right, so this one equals x minus y and mod y. Okay, we'll continue. So my mode is also an operator, built-in operator. So we cannot name a function mode. All right, so we name it my mode. Okay, y. Okay, so this one equals x. Okay, if less than xy. All right, again a condition. Once you have this if part, then you need this arrow to say, oh, where no further condition. If there are conditions, then you can write the conditions on the right hand side of the rule. And my mod xy, okay, equals, this one is my mod sub xy and y. All right, good. So we have this basic operations. All right, next let's consider exponent function, the power function. All right, so x to the power of y. All right, this time we recurse on y. So if it's 0, okay, this one equals 1. All right, 1, what is 1? 1 is basically the successor of 0. Okay, x to the power of y. Okay, then what do we do? All right, we implement this power function by using multiplication. Okay, so this one equals x times and x to the power of y minus 1. All right, so let's say power whatever x is, and if the second one is exponent is 0, okay, then the result is 1. 1 is basically s0. Okay, and the power this one xy. Okay, this one equals multiplication x and then power x and then predecessor y power. All right, good. Okay, maybe next factorial. All right, let's say factorial function. A factorial function. Okay, factorial function. Let's call it fact. Factorial function. Let's say n. All right, n equals. Okay, we can write this. Factorial function. This one equals 1, and the factorial function is n equals n times factorial n minus 1. Good. All right, basically this is the program. Yeah, this is the program. We don't need to write the comment. Okay, fact 0 equals 1. All right, so let's say s0, because in our world, okay, there is no such a constant called 1. So and factorial n is n times factorial n minus 1. Okay, good. Next, let's consider the Fibonacci function, fib. All right, fib 0, okay, equals 1. Fib 1 equals 1. And fib n equals fib n minus 1 plus fib n minus 2. All right, that's Fibonacci function. Okay, and the last example is a binomial coefficient. All right, binomial coefficient BC. Let's say BC. N choose K. Well, basically, you have a set of n objects. You want to choose k objects. Okay, binomial coefficient gives you the number of different ways, okay, to choose k from n. Okay, so this is okay. If k is 0, all right, no matter what the first one is, okay, there is only one way to choose it. And n choose n, okay, there is only one way to choose it, n k. All right, this one equals BC. Okay, you pick an object. All right, you keep it. There is a choice. You keep it or you don't keep it. If you keep it, then you still need to choose k minus 1 objects from the remaining n minus 1 objects. If you don't keep it, okay, then you need to choose n k. Still need to choose k objects from the remaining. All right, good. Hopefully, I didn't create any typos. All right, let's run the program. Okay. Start the system. CL none. There is redefine. Oh, power is a built-in function, is it? No. Oh, it is a built-in function. Okay, so let's rename it. Okay. Okay. Let's rename it, called my power. All right, looks good. Okay, let's say, okay, we test the predicates, test the implementation, and say add. All right, add for 5, and let's say z equals, okay, what is this, 9, and sub. Okay, of course we cannot get a negative number, so 5 minus 4. All right, it's 1. and multiplication. Okay, it looks good. Okay, my div. Alright, this is good. And my mode, and then power. Okay, power. Okay, looks good. And next, okay, let's do this. This one Fibonacci function. Well, since the Fibonacci function, as it is defined, it takes exponential time to compute, so we cannot compute a large, number. Okay, a Fibonacci number. Okay, so this one is fine. Okay, binomial coefficient BC. BC, let's say 5, choose 4. Okay, choose 3. All right, good. And now let's go back to the program. Okay, now. All right, so let's try to improve the efficiency. Okay, in functional programming and logic programming, sure, we use recursion to describe repetitions. Okay, but recursion, as you know, incurs some overhead. All right, each time you make a recursive call, all right, you need to have a frame pushed on to the runtime stack, and it takes time and costs and also consumes space. So, and functional programming and logic programming systems perform an operation called tail recursion optimization, which basically converts tail recursion to iteration. Okay, so that means okay, for tail recursion, okay, you don't need to pay the price. All right, because the same frame is reused. Okay, again. All right, so let's convert some of the functions to tail recursion. Okay, what is tail recursion first? Okay, a function or a predicate is tail recursive if the last call calls the definition itself. Good. So for example, this addition is not tail recursive. Okay, why? Because the last function call is the successor function. Okay, so which is different from the defined function add. All right, let's make it tail recursive. So add 0. Actually, for this one, it's pretty simple. Okay, let's call it add faster. All right, faster. Add faster, and this is x, y, and what we could do? Okay, we could do something like this. Okay, predecessor x, and then successor y. Okay, we can do this, and then this one becomes tail recursive. Okay, very nice. Okay, how about subtraction? Actually, subtraction, we can do something similar. Subtraction, okay, let's name it faster. X 0 equals x. Sub fast x y. All right, so what we could do? Okay, this is basically x minus 1 and then minus y minus 1. All right, so we can do something like this. Okay, so this is the predecessor of x and then minus the predecessor of y. All right, then this one becomes tail recursive. Very nice. All right. How about multiplication? Multiplication. This one we cannot just do what we did before. Okay, to convert this into tail recursive. What do we need to do? We need to count. Yeah, we need to count how many times. Okay, we have done addition. All right, we have done addition. So we need to introduce a help function. All right, so let's say more faster. All right, so this is x, y. Okay, we introduce a help function. Okay, let's call it mal_x. Okay, x, y, and which takes an accumulator. In the beginning, how many times we have added? Okay, we have performed addition. Okay, 0 times. So this help function is defined as okay, if the first one is 0 and then this one. So x times 1. If the first one is 0, okay, this is ACC, okay, then the result is ACC, okay, basically number of times, number of additions. And x, this is x, y, ACC, this one equals, okay, so this is amount x, this is predecessor x, and then we do addition. Yeah, we add y. Okay, instead of adding y to the final result, we add y to the accumulator. Yeah, okay, to the accumulator. So y, and we say add y to the accumulator. This becomes a new accumulator. Okay, good. So then this one becomes tail recursion. Similarly, we can do other. Okay, we can do other we can convert. Yeah. Of course, let's say we add in the tail recursive version. We all use add faster. Right? Add faster. All right. So add is tail recursive, and then we can do a comparison. Yeah. Okay, we can. All right. So let's say. Good. All right, we can say add faster 4 5. Okay, and sub faster and multiplication faster. All right, of course you don't notice any difference. All right, so the time, okay, because the numbers are very small. Let's try some larger numbers. Okay, let's say 500, and this is okay, 500 times 4. Good. I think it is still faster and not big enough. 5,000. All right, let's try the slow version. Okay, still okay, larger, even larger. All right, then it takes time a little bit. Okay, we can measure the time. All right, let's see how much time it takes to do this. Okay, it takes 0.422 seconds. All right, how about the faster version? The faster version. All right, it's pretty fast. Okay, it's a little bit faster. Well, because it's still recursive. Yeah. Okay. All right. Next, let's say Fibonacci. Okay, this Fibonacci, well, as it is defined, okay, so it takes exponential time to compute the Fibonacci number of a given number. Why? Because okay, because for each core it generates 2 function calls. All right, so it is exponential. Okay, same here. There's binomial coefficient. All right, it's exponential. Okay, so we cannot. Let's write. Also faster version. All right, faster version. All right, and also this binomial coefficient. Okay, we have faster version. And also, what do? We use dynamic programming. Okay, we just add a table in the beginning. So this one, okay, all sub-problems, okay, will be tabled together with their solutions. Okay, so it is very easy to do dynamic programming in Picat. All right, now let's say Fibonacci. Okay, this is 30. Let's try 30. All right, let's say x equals f Fibonacci. Good. All right, it's time. All right, so okay, let's try the faster version. Oh, it's 0 second. Okay, actually you can go faster, much faster. Yeah. Okay, Fibonacci of 300. Okay, so you get it instantly in 0 seconds. Okay, so you see how powerful dynamic programming is. All right, let's try binomial coefficient. Okay. So binomial coefficient, let's use n. Okay, BC, this is a slow version. Okay, let's say 300. Okay, we want to choose 5. Okay, choose 5. Oh, that takes too long. This takes too long. Yeah, cannot try this. Okay, it takes too long. Okay. 300, choose 5. Okay, wow. It takes too much time. Okay, let's try the faster version. Oh, it comes right away in 0 seconds. All right, so today we talked about recursion. Okay, we talked about the importance of writing tail recursive functions, and also the idea of dynamic programming. Okay, if there are common subproblems, okay, then okay, it is a very good idea. Dynamic programming is a very effective. Okay, thank you for watching.